artificial intelligence. Once a figment of science fiction, now a ubiquitous force. AI powers our smartphones, guides our cars, and even composes music. Yet this triumph was not always guaranteed. In the 1980s, a colossal flop in AI research threatened to derail the entire field. Ironically, this very failure sowed the seeds for the AI revolution we witness today. The 1980s witnessed the dawn of the digital age. Personal computers, once a novelty, began to populate homes and offices. The internet, still in its infancy, held the promise of global connection. Amidst this technological ferment, a bold AI initiative emerged, aiming to leapfrog existing technologies. This initiative, known as the Fifth Generation Computer Systems, or FGCS, was spearheaded by Japan. The goal was ambitious: to create a new breed of computers capable of human-like reasoning and problem-solving. The FGCS project was audacious in its scope. It sought to move beyond the limitations of traditional computers, which excelled at crunching numbers, but struggled with tasks like natural language processing and image recognition. The vision was to create machines that could understand and respond to human language, learn from experience, and make complex decisions. To achieve this, the project focused on logic programming, a paradigm that emphasizes symbolic reasoning and rule-based systems. Massive funding poured in, and the world watched with bated breath, eager to witness the dawn of a new era in computing. Section 4. Stumbling blocks. Why FGCS faltered. Despite its lofty goals and significant investment, the FGCS project ultimately fell short of its ambitions. The initiative, launched with much fanfare in the early 1980s, aimed to revolutionize computing by creating machines that could think and reason like humans. The project faced numerous challenges, both technical and conceptual. The ambitious goals set by the project leaders were often at odds with the technological realities of the time. Logic programming, while theoretically elegant, proved too rigid and computationally expensive for real-world applications. The limitations of the hardware available at the time further compounded these issues, making it difficult to achieve the desired performance. Moreover, the project underestimated the complexity of human intelligence. The nuances of human thought and the intricacies of cognitive processes were far more challenging to replicate than initially anticipated. Tasks that seemed straightforward, like understanding natural language, turned out to be incredibly intricate, reliant on vast amounts of contextual knowledge and nuanced understanding. The FGCS project struggled to develop systems that could handle the subtleties and ambiguities inherent in human language. By the early 1990s, the limitations of the FGCS approach became painfully apparent. The gap between the project's aspirations and its actual achievements was stark, leading to widespread disappointment. The project, once hailed as the future of computing, was widely perceived as a failure. The lessons learned from FGCS, however, paved the way for future advancements in AI and computing, highlighting the importance of realistic goals and adaptable methodologies. Section 5. A new dawn for AI embracing practicality. The downfall of FGCS, while a setback, proved to be a valuable lesson for the AI community. It underscored the importance of adaptability and the need to pivot when faced with insurmountable challenges. The AI community realized that clinging to a single approach could hinder progress. It highlighted the limitations of relying solely on symbolic AI and top-down approaches. These methods, while groundbreaking at the time, were not flexible enough to handle the complexities of real-world data and scenarios. Researchers began to explore alternative paradigms such as connectionism, which sought to mimic the brain's structure and function using artificial neural networks. This new approach aimed to create systems that could learn and adapt, much like the human brain. This shift in perspective coincided with the rise of the Internet and the availability of vast amounts of data. The Internet revolutionized access to information, providing a rich resource for training and developing AI models. This data-driven approach, combined with advances in computing power, breathed new life into the field of AI. The synergy between data availability and computational advancements enabled researchers to tackle problems that were previously thought to be unsolvable, paving the way for modern AI breakthroughs. Section 6. From backpropagation to big data, the building blocks of modern AI, the post-FGCS era saw a surge in research on artificial neural networks. One crucial breakthrough was the development of the backpropagation algorithm, which enabled efficient training of multi-layered networks. This paved the way for significant progress in areas like image recognition, speech processing, and machine translation. The availability of massive datasets, coupled with increased computing power, further fueled the AI revolution. Machine learning algorithms, particularly deep learning models, thrived on this abundance of data, learning to identify patterns and make predictions with remarkable accuracy. As Section 7, Lessons Learned, Progress Made. The legacy of FGCS. The FGCS project, though ultimately unsuccessful in achieving its stated goals, left an indelible mark on the field of AI. Initiated in the early 1980s by Japan, it aimed to leapfrog the existing computer technologies and create a new generation of computers that could perform at the level of human intelligence. Despite the ambitious goals, the project faced numerous technical and theoretical challenges that were insurmountable at the time. It served as a powerful reminder of the importance of pragmatism, adaptability, and a deep understanding of the complexities of intelligence. The FGCS project highlighted the gap between theoretical AI and practical applications, pushing researchers to rethink their approaches. It underscored the necessity of incremental progress and the value of learning from failures. The lessons learned from this failure spurred the development of new approaches and technologies that form the bedrock of modern AI. Researchers began to focus on more achievable goals, leading to significant advancements in machine learning, neural networks, and data processing techniques. These innovations have paved the way for the AI technologies we rely on today. Today, as we stand on the cusp of a new era of AI-driven innovation, we owe a debt of gratitude to the ambitious, albeit flawed, visionaries of the FGCS project. Their pioneering spirit and willingness to tackle seemingly impossible challenges have inspired countless researchers and engineers. Their legacy lives on, not in the form of thinking machines they envisioned, but in the transformative technologies that shape our world today. From smart assistants to autonomous vehicles, the influence of